Saxon Advanced Mathematics, lesson 93. We are at the beginning of our last week here before the midterm. The midterm, we'll do a normal week this week. Then next Monday, which is March 28th, I will drop a review video for the midterm. You'll have a couple days to study, and then I will deliver the midterm to your house on Wednesday around noon, and then I'll be back to pick it up Thursday, probably more like 2 or 3. I'll give you a little bit more than 24 hours. Same as always, 10 problems, same format, 5 points each. Once you take the midterm on March 30th, you will have the next week off for our spring break, and then we will meet again on April 11th. No homework is due that date, but that's when the new videos will drop. Here's our spring schedule. We only have 6 weeks of spring. Amazing. If you are preparing for Running Start and you want to take your college placement test, that usually happens in May. So what we're going to do is we're going to have a couple weeks of intensive preparation and review before that test. So if you're preparing for college next year, you'll just go through 100 and then we're going to switch gears, all right? I will continue to post the regular lessons up through 120 for students who just want to fully complete this course of study. But if you're preparing for the Acute, which is the test we'll be preparing for, then we're going to stop at 100 and switch gears. Okay, two-parter in lesson 93. The first part is advanced trig identities. So there's still trig identities where we're trying to make the left side look like the right side. This is our tip. In both of these problems, I think it's just 2. No, there's 3. In all 3 of these problems, the trick is to look at the denominators and use that to plan your strategy. So let's look at the first one. Okay, so here's what we've got. We look at the denominators and think, how are we going to turn this into this? Well, we're not quite there, but the first thing that jumps into my head, and granted, you guys, this is the hard part of these identities, is having these brain flashes where you see this. I know that cosine squared b equals 1 minus sine squared b, right? That makes this side kind of look like that side, but I would have to turn this into a square, wouldn't I? Because right now I just have plain cosine of b, and in order to change it, I need to have this. That's what tells me, hey, why not try multiplying the left side by cosine of b over cosine of b, right? So that's what I'm going to do. I'm going to take our original expression and in order to get that square, I'm going to multiply it by cosine of b over cosine of b. Just because I want to get a square on the bottom. So let's see what we've got now. This will be cosine squared b, right? And then that is equal to 1 minus sine squared b. So I'm going to substitute this in instead. Then I know, oh, this is a perfect square. And I can factor a perfect square thusly. Whoops, that needs to be a minus. Right? So now I'm going to use this factoring pattern on this. One's a perfect square and that's a perfect square. So I'm going to leave the top the same. Cosine of b times 1 plus sine of b. And then this, I'm going to factor using this. 1 minus sine of b, 1 plus sine of b. I can write it in either order, right? As long as I have a plus and a minus, I'm fine. It doesn't matter which one's first. Beautiful. Now I can cancel the pluses and look at my final answer. I'm just going to rewrite it so you can see it clearly. Cosine of b over 1 minus the sine of b. And that is exactly what I was going for. Yay! Now, again, it's so much easier when someone else is coming up with the ideas, right? But the trick is to look at the denominators, and that's what I did here, and I saw, boy, if I can square this and use this, then maybe I could get to that. I knew this form was a lot closer. All right, so that was my thinking there. Let's try another one. As I write the problem out, I'm just looking at the pieces of it and thinking very generically about what I'm looking at. There's nothing intense happening here. But I'm just kind of looking at the pieces and noticing the patterns. Oh, this is minus. I did it again, didn't I? Okay, here's what I noticed. Look, the forms of these fractions are pretty similar, right? Because this is something plus something, and then the same something minus the same something. Same thing is going on over here, right? Something plus something, the same thing minus the same thing. That pattern's the same, so I know I'm not going to have to change this too crazily. I know that I can restate everything in terms of sine and cosine, right? Because this is tangent equals sine over cosine, and secant equals 1 over cosine, and cosecant equals 1 over sine. Okay, so maybe there's a way. I'm going to rewrite this denominator only. It's 1 over the cosine of b minus 1 over the sine of b, right? This is another way of writing this denominator. So I'm going to put that there because if I could get this to look like this, then I know it's an easy jump just to change it to the reciprocal functions. These are all puffies. These are all identities, right? This is called our quotient identity, and these are called reciprocal identities. They're all on our page. Okay, so what I'm going to do is I'm going to start by changing this out to sine over cosine. So this will be sine b over cosine b plus 1 over sine b over cosine of b minus 1. Okay. So far, so good. I want the denominator to be changed to 1 over cosine of b. So I don't have a grand strategy in mind. I don't know how this is going to work out, but it seems to me that if I multiply this by sine over b, 1 over sine over b, then these guys will cancel, and I'll have 1 over cosine of b where I want it, right? Now, the only problem is, in order to do this, I'm going to have to multiply top and bottom, and I'm going to have to distribute that 1 over sine of b, aren't I? There's going to be a lot of multiplying going on. So let's try that though. This one cancels, and I get, let's see, I'm on the bottom, 1 over cosine of b, and then it will be minus, and I'm multiplying 1 times that, so it's just 1 over sine of b. And on top, these cancel, and it's plus, and then the second one. And look what happened. Our denominator matches to the other version of this. And I see the top is perfect too. Now all we have to do is restate all these fractions with their reciprocal functions, and I think I'm going to have it. 1 over cosine of b is secant, plus 1 over sine of b is cosecant. And then in the denominator, minus. And look, this is what we're going for, right? And this is what we got. We did it. Yay. All right, and again, it all came from looking at the denominator and comparing what we have to what we want in the denominator and trying to make changes that would lead us in the right direction. So that was our first step, to turn tangent into sine over cosine. That's how we first broke it open. Okay, let's look at the third one. Which is a creature all its own. And it's kind of long. Ooh, that was a squeeze. All right, let's take a look at what we have going here, because it's pretty crazy, isn't it? Oh boy. Okay, so we've got a beast that we're squaring, a beast that we're squaring, and we want that to be equal to this. This is the left side. Look at the left side, doesn't have any sines or cosines in it. It's just these coefficients that we have on the trig functions. We haven't looked at this in an identity situation before. We've never seen anything like this. We've never had squaring binomials in trig identities. We're crossing into a lot of uncharted territory. So let's start with what we know. Let's square both of these binomials. Because somehow all of these trig functions are going to have to cancel out, aren't they? Okay, so let's start by squaring the first one. We'll call this step 1. We're going to do x times the sine of theta plus y times the cosine of theta. That times itself. Oh boy, okay. So let's see what we've got. The x's square and the sine square, but we don't have to put a square in front of the theta. This whole thing squares like that. That's how we make the notation. Plus, and here's the way we square this. We put the x and the y together, and then the sine and the cosine. Oh, I should have a theta in there. Sine of theta, cosine of theta. Okay, so now we've multiplied those two. Now let's multiply these two. X, y, sine of theta, cosine of theta, plus y squared. That's how we square those. Let's add it all up and see what we get. Plus 2xy wait, it's not a squared. I saw that little theta up there and I copied that as a squared, but it's not squared. We're just adding these, so we have 2 of them. So this is the first binomial squared. Now we have to do the second binomial squared and then combine them. Right? Now, what I'm thinking is, I don't want to copy this all over again because I'm going to have to add them, right? So I'm going to make space right here to where I'll write the second one, but I'm going to square the second one on another piece of paper. You're probably writing smaller, so you can just go down the page. But I'm writing so big that I'm running out of room. Okay, so what I'm going to do is I'm going to leave space here to finish the problem, but I'm going to square this binomial on this second piece of paper. So this is going to be calculation 2, x times the cosine of theta minus y times the sine of theta, right? And then I do that twice. And now we do the dance. I start here and I go up. We get x squared and we get cosine squared. Now I multiply across. I have minus, and I do the 2 coefficients and then the 2 trig functions. Excuse me. All right. Now it's time to go this way, and I get the same thing here. It's minus xy sine of theta, cosine of theta, and then here at the end, I'm going to get plus y squared, sine squared, squeeze in a little bitty theta. Ready to add? Remember, we're adding these, so we have 2 xy sine of theta, cosine of theta, and then our last little bit plus y squared, sine squared, theta. Okay, this is my answer for the squaring of the second binomials. I'm calling this 1 and this 2. Now I'm going to copy my answer for the second binomial squaring right here. I'm adding it. Let me double check and make sure that's right. I'm adding it. So I'm going to leave all the signs the same. Okay, so this multiplication I copied over to right here. Now we're ready to add these two together, right? Now, let's see. I'm going to have x squared sine squared theta plus x squared cosine squared theta. Now look what happens to these middle terms. Happy days plus minus. These two cancel out completely. Oops, I went too far with that one, sorry. Then we have these two at the end, plus y squared cosine squared theta plus y squared sine squared theta. Woo, squishing it. Now, what I recognize is that I can factor here. I can pull the x squared out, and then I can pull the y squared out. And what I'll have is x squared, and then I'll have sine squared theta plus cosine squared theta. Right? That's the remaining pieces when we pull the x squared out. Plus, and now I'll do the same thing here. And I'll just write it so it's in the same order. I'll put the sine squared first. Right? Okay, good, good, good. Now we need our Pythagorean, right? Because it tells us that sine squared theta plus cosine squared theta equals 1. And I'm looking, here we go. I just want to show you that. Here it is. Sine squared theta plus cosine squared theta equals 1. It's the very first of our Pythagorean theorems. So that means that this goes to 1 and this goes to 1. And so, because I'll write it up here, cosine squared theta plus sine squared theta equals 1. That's what we're using down here. I would write it down closer to where I actually used it, but I'm fresh out of space. All right, and so that gives us x squared plus y squared, just as we hoped. All the trig functions canceled out, and we got just what we're looking for. Whew, that was a doozy. We didn't need to use a trig identity till the end. The trickiest part with this is that we had to face the music and square those binomials, and that was kind of intense, right? I agree. Okay, let's move on to the second part of this lesson, which is talking about triangle inequalities. This is a quick and easy little side calculation that is easy to understand. I mean, considering the monstrous beast we just worked, this is like a piece of cake. Okay, when we have a right triangle, we know that we can use this little friend called the Pythagorean theorem. A, B, C. We know that a squared plus b squared will equal c squared. That is when we have a right triangle. But what if we don't have a right triangle? What if we have an obtuse triangle? Okay, well, we still know this is the longest side. This is the hypotenuse-like side, right? And this, we'll call this A and this B. And I want to rearrange this just a second. C equals a squared plus b squared. That's the same thing, right? In an obtuse triangle, there is still a relationship between c squared and a squared plus b squared, but it looks a little different. Oops, I forgot the square there. C squared is greater than a squared plus b squared, which kind of makes sense when you look at the picture, right? You can see that that's really long, and it makes sense that it's bigger than. And then the third part of this, and it's a lot harder to tell which is the longer side, but you pick the longest side. This is an acute triangle. And in this case, c squared is less than a squared plus b squared. All right? So we can categorize triangles as right, obtuse, and acute simply by looking at this pattern among with their sides. All right? So that's what we're going to do in these problems. There are two of them. We're going to use these relationships, right? If c is equal, if c squared is equal to a squared plus b squared, it's right. If c squared is greater than the other two sides squared, it's obtuse. If c squared is less than the other two sides squared, it is this. And then a little hint is let c equal the longest side. Because there's nothing, it doesn't look like a hypotenuse. Okay, this applies to this type of triangle too. It's just that in here, this one is pretty easy to see which is the longest. All right, so we're going to take these rules to some calculations. Ready? 93.4. Is the triangle whose sides are 3, 4, and 5 a right triangle, an acute triangle, or an obtuse triangle? All right, well, we know what to do. We let C equal the longest side, and then we compare 5 squared, and what I'm going to do is I'm going to just, how do I want to do it? Sometimes I draw a box, and I know that greater than, equal than, or less than is going to go in there. 3 squared plus 4 squared. Okay, this is 25. Is it greater than, equal to? This is 9 plus 16. That equals 25. So 25 equals 25. So that means that this would be a right triangle. Because when c squared equals a squared plus b squared, when they're equal, that's a right triangle. Okay, cool. And one more. Classify the triangle whose sides are 4, 7, and 5. Okay, again, we know that this is going to be the C. This is the longest. So we'll have 7 squared and then a box that we'll fill in with greater than, less than, or equal to. And then the other two sides squared and added together. 16 plus 25 equals 41. 49 is greater than that. So that tells us, when we check our list here, it's greater than, so that means it's an obtuse. Pretty straightforward calculation. I mean, super easy calculation, right? The only thing that's tricky is just remembering these patterns. Although I think once you have this straight in your mind, which I'm pretty sure you do, it makes sense that an obtuse triangle, this hypotenuse, is going to be longer than a right? Because it pushes out past. So this one's pretty easy to remember. And then acute is just the other option, right? Equals, greater than, so acute has to be less than. Remember to let C equal the longest side. Okay, guess what? Dun, 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 dun. We're all done. Thank you, goodbye.